right into some notes. What I've got set up here is essentially a kind of template for a typical question involving hypothesis test with two different proportions. And then after that, we'll go back and have a look at some homework questions. So here's my story. Pretty standard one. It's the kind of thing they actually do in, the real world. You've got two possible treatments, say, for cancer. Maybe you've got an old treatment. Now someone's figured out a better way, or hopefully a better way. Well, you have to test it. You can't just take a doctor's word for it. They may have spent years perfecting it, and it may not work any better, at least, than the other stuff. So they conduct a clinical trial. This particular one doesn't look like it has anything blind going on, but it could be possible. You could, if the treatment just involved various injections and pills, you could certainly not tell the patients which version of the treatment they're getting, and the doctor that is their primary caregiver doesn't know either, but they can collect the data that way. But continue with the story. How do you tell if one's better than the other? Well, you do a clinical trial, you do an experiment. In this one, 200 patients undertook treatment A. Success rate was 75% for the cancer treatment. 400 undertook the other treatment, we'll call it treatment B, and the success rate was 78%. In the medical world, success rate is judged in lots of different ways. One of the ways they can judge success rate is what percentage of their patients are still alive after 5 years, or maybe even just after 6 months. In other situations, a success rate would be a complete cure. In other words, there is no cancer that is detectable, right? So whatever the success rate measured, 75 for the first stuff, 78 for the second. So superficially, treatment B looks better. But, that could just be randomness. That's why we have hypothesis tests. So we're going to try and see, is there enough evidence to conclude that treatment B, obviously it's a bit bigger, is more effective than treatment A? And we're going to do it with a significance level of 0.01. So that's a pretty standard looking question. Now I'm going to do it a little bit different than the typical way that I would do it. Hold on a second, just get myself organized because I had to close all my windows to get this thing to work. Is that we're going to do a little bit more calculation by hand than we typically would. Almost everything that I'm doing up here, you could certainly get by just using Solve. But I want to show you how you do it the long way, right? The good old-fashioned way as well. At least for the parts that we can actually use calculators on. So first part of the puzzle is this. I'm just going to take this information and we're going to transfer it over here. So what have we got? For the first group, there are 200 patients and their success rate is 0.75. And for the second one, there are 400 patients and the success rate is 0.78. We're going to calculate the standard error of the difference. You've recognized this ugly formula. It's going to be the square root of 0.75. One takeaway, that gets you 0.25 divided by 200. And then in the other case, it's 0.78. 0.22, and that's going to be divided by 400. And so I'm going to go here and it's the square root of this guy plus that guy. So 0.75 times that fella divided by 200, add 0.78 times that fella divided by 400, and I am looking at 0.037. Well, at least the 3 decimal places I am. We're pretty comfortable about that, where all the information came from. You recognize that big ugly formula, the standard error guy. Now, there is a fella that we have kind of superficially been ignoring and just saying, you know, it's in SALT, just use it. And that's the test statistic, which in this case is a Z-score. If you're ever wondering where does it come from, here is the actual formula that you could do without going near SALT. It's P1 take away P2 hat, so it's the difference between these two, divided by the standard error. So in this particular case, it's going to be a 0.75 take away a 0.78, and it's going to be divided by 0.037. And that's definitely going to be a negative number. If you're doing this at home kind of thing, don't do this. I'm about to do it wrong, just to show you why you have to be careful with calculators. So 0.75, so this is going to be wrong. Take away 0.78 divided by 0.037. And the answer I get is ridiculously large number of -20. Does anybody know what I did wrong? Why that is not the correct answer?
Order of operations.
Yeah, you need to stick a bracket around the top guy. Order of operations. In other words, you need to do the top before the bottom. And hopefully I got this guy sorted out. And we get -0.811, at least to 3 decimal places. This Z-score is the same Z-score that we've met in lots and lots of places. Can you remember what kind of Z-score is unusually big? What kind of number would you get if it was an unusually large Z-score?
Would it be like 3?
Yeah, and the other side, -3, right? So if you don't see an unusually large Z-score, that's because whatever it is you were looking at wasn't that unusual, right? So I can make a prediction that this particular one is not going to be significant, right? Now, the next stage would be p-value, but there comes a point in time where it's just not feasible to do it by calculator or hand, or at least not easy to do it by that. So at this point, I'm just going to let SALT take over. And I'll click on a random SALT button. Oh, shoot in space. Okay. I am not going to swear. I'm going to be really good and not swear. When I hit the SALT button, my questions disappeared. It's really annoying when it does that. I'm not quite sure why it does that. Oh, it's over here now. What the heck are you doing over there? Gotcha. Okay. Okay, so let's put that information into SALT so we can get the p-value. So with a bit of luck, you are looking at SALT. Is that correct?
Yeah.
Okay, so in this particular world, this particular one, isn't it 2 sample proportion? Oh, I didn't calculate that, but I've got my calculator handy. Don't we have to find out how many people for treatment A, which is 75% of 200? And can you trust me that that's 150 people out of 200? Are you comfortable with how I got the 75% and turned it into 150 out of 200 people? All right. Now, the other one was 78 out of 400. That one I can't really do in my head, so I'm calculating it here. That's 312 people out of 400. And we are interested in the difference, right? Which is always zero when you do a hypothesis test for the difference of two proportions. And we want to find out if the first guy is actually less than the second guy. Now, the sentence said, is there enough evidence to prove that treatment B is more effective than treatment A? Right, that's the way it was phrased. But the logic of it is, don't you have to do it in terms of the difference between the first and the second? So if the second one is better, doesn't that mean that the answer has to be less than zero? P1 take away P2 has to be less than zero. So that's why that's there. It's equivalent. John is taller than Mary. Mary is shorter than Tom. Isn't that the same information written from two perspectives? Right, so that's what that little guy there. Right, generate results. Do you see my negative 0.8? Now, do you notice it's a little bit different than the 811 that I said it is 823? Have you any idea why there's a little difference? It's a pretty obvious reason.
Rounding.
Yeah, rounding. They are doing 6 decimal places. I was rounding all over the place to 3 decimal places. Can you see there's a little bit of discrepancy because of that? Now, there is our p-value. So that's the guy that we were after. And I'm writing them down right now, 0.205. Again, I'm writing it down to 3 decimal places. Oh, by the way, do you see the standard error? Then I have 0.037. Would you agree that's pretty close to what they had? Just rounding off again. You know, I had 0.037, they have 0.036445, and so on. So doing it by hand, if I wanted to get that accuracy, I went around different 6 decimal places, and I'd be fine. So let's return now back to that question. Here is our p-value. Not particularly small, but I wasn't expecting it when I saw the z-score, right? So is our p-value less than this fella? Well, is it less than that guy? Well, it's clearly no, right? So what's the conclusion going to be then? If your p-value is not less than your significance level alpha, what conclusion do you come to?
There's not enough evidence.
I'll say to reject H naught. But they might say to reject the null hypothesis or another phrase that is essentially the same. Can you imagine that that entire clinical trial could easily have cost $500,000? And the pharmaceutical company that was producing maybe the treatment, right, the chemicals and the, you know, the injections and the pills, whatever it was for this new treatment, they've got nothing out of this, have they? Because their new treatment isn't any better. I guess it's not any worse, so that's good, right? But it's not any better. And so what would happen if they tried to get the FDA to agree to this as a new treatment, is that the FDA would reject it. Not because it was unsafe, because that part has already been done. The normal way that things happen is that you start off with a new treatment, a new drug, and the first trial that you do is very often a very basic baby one, just to see if there's any bad side effects. You know, does it kill people? Right? That's not a very good clinical trial to be in. They're not normally testing how effective it is, just does it kill you, or does it have really bad side effects that are worse than the thing you're trying to treat? That's the first hurdle. And you can spend a fair chunk of money doing that. Then the next hurdle is this one. You have to prove to the FDA that your thing is at least better than whatever else is out there. Because if it's no better, there's no point in them introducing, can you imagine 20 different cancer treatments that are all just as good? Why do you need 20? If one's going to have the same success rate as the other 19, just have one. And what does that do? Well, you know, when people have different illnesses, there's all sorts of interactions between the chemicals, you know, the pills that they take. If you reduce the number of treatments, don't you reduce the number of possible bad interactions because there's fewer of them? So the mindset of the FDA is, nope, if it ain't any better than the old one, there's no point in us doing it. So this poor company would have to say, okay, what could they do? If they really truly believed that treatment B was better than anything out there, even if it's only a few % better, that's a few thousand lives. You know, that's a lot of lives. What could the company do apart from cheat and lie? There's only one practical thing that they can do.
I don't know, try and prove it somehow.
Yeah, do it again, but with one change. Do the same clinical trial a second time, but with one major change.
More patients.
More patients. If you made the 2,000 and 4,000, right, you upped it by 10 times. You may find, but you'll say, well, it's still 75 and 7. Let's pretend it still ended up being 75 and it still ended up being 78, right? Just imagine that that was the case, but now it's for 2,000 and 4,000 patients. If you went through the calculation, right, and you upped it by 10, let's pretend that we did that, right? We did the same trial again, but this time 2,000 and 4,000, and we got the same percentages, 75 and 78. You might expect that all these numbers, especially the p-value, won't change because the percentages never, so surely that should mean that. Well, no. Let's show you the new improved clinical trial, at least from the perspective of the pharmaceutical company. Can you trust me that that would now become 1,500 out of 2,000, right? That's 75%. And this would become 3,120 out of 4,000, right? That's all I've basically done is up everything by a factor of 10, right? Everything else stays put, right? Generate. Do you see that test statistic is now that number? And can you see that your p-value is now less than 0.1, 0.01? So if all things remain the same, right, the percentages didn't change, can you see the benefit of a bigger sample? If there was a true difference, it would show up. So what the pharmaceutical company might do, and it's a kind of gamble, they might say, okay, that cost us $500,000. Do we want to spend 5 million more in doing a bigger one? Right? Let's do a really massive clinical trial. And then they could say to the FDA, hey, 3% is 3%, you know, 100,000 people get this cancer a year, we can save 300 more, or 3,000 more, I should say. That's a pretty good deal, right, if it works. And what would typically happen then is that the new treatment B would become the go-to treatment for that particular cancer. And that's how the medical field advances. You prove that what you're doing is better than what you used to be doing. But it's done in a very structured way, right? That's the strength of hypothesis testing, is that it takes away me saying, I truly believe this new treatment is better. Right? That's not evidence at all, right? Number crunching is evidence. Are we good with that? Did you like the process? Right. So let's just nip back now and see what we can do with these homework questions. Okay. There we go. I'm going to zoom over here. I kind of need you lot to tell me, yeah, we've done this one, because some of these questions kind of get repeated in different places. I believe we did yesterday the one to do with men and women returning money, and we found out women were more honest. That one I'm pretty comfortable we did before. What's this one about? Yeah, this is a new one because I get rid of some questions and I replaced it by this quite long-winded one, but let's see what it's like. During the coronavirus pandemic in the spring of 2020, restrictive measures were enacted to keep people from interacting with each other in public places, you know, like 6 feet apart, wear masks, all sorts of rules like that. You know, wash your hands all over the place, all good things, I'm sure. Polls asked the following question in the third week of April. And then they went and asked them in the second week in May. So basically it's a before and an after opinion to see if things have changed. And the question they asked you was, do you think the current restrictions on how restaurants and stores and businesses operate in your state are appropriate, are too restrictive, or they're not restrictive enough? So you give them like a 3-choice deal. Yeah, it's about right. Nah, too restrictive. Nah, they should do more, right? That kind of choice. In April, oops, let's get, almost lost a place there. Different random samples of 1,007. I better write that down because I'll forget the numbers. It was basically a standard, you know, survey or a poll. And the first sample was 1,007 people. And it was used for each poll, okay? So the second time they did it, it was still 1,007, that seems fair. In the April poll, 18% said it was not restrictive enough. So p hat 1 is 0.18, that's 18%. While in May, 22% gave that answer. God, I wonder what state that was. Well, it is what it is. Did the proportion of population who thought the current restrictions were not restrictive enough change? Yeah, looks like it went up. They told us the Z statistic, -2.24, and they even told us the p-value. So can you see in this question, you don't need to go through SALT at all, because the minute you tell me that, that's pretty much everything I need to know, isn't it? I've got a p-value. Great. Right, now, what was P1? Well, of course, I got the answer here anyway, but I'll call that off for the next one. P1 is the population proportion in April who answered not restrictive enough. Yeah, that was true. What was P2? That was the people who did it in May. And let's get rid of these darn answers. I'm sure stop doing that. So we answered those two because of there. Now, the null and alternate in this story. We're going to do a P1 take away P2 equals 0 because it's always going to be that. So here's my P. Can you remember where that subscript was heading? Where was, because I'm going to do P little baby 1, right? P subscript 1. Where's it hiding?
It's in functions, isn't it?
Yeah, right up there. So it's one of those kind of, that's what it is, right? P1, take away P2, and it's going to equal 0. And for a difference between two proportions, remember yesterday we talked about this, isn't that always the null hypothesis, at least for the ones we do? So you don't have a choice. Just always stick that one in, you'll be safe. Now, the alternate here is that if you took the April results, try that again, just copy the whole thing. Now, less than, bigger than, or not equal to, that's your three choices. What is it in this story? P1 was April, P2 was May. Can you remember April was 18, May was 22? Greater than, less than, or not equal to?
Not equal to.
We are being asked, let's see. And they use the word change. You see that? If they'd said got bigger, wouldn't we say greater than 0? If they said got smaller, wouldn't we have said less than 0? But if they said just change, then we put in not equal, which I believe is this funny X, oops, try again. Is this funny X? Why can't I do exclamation mark? There we go. Not equal to. Right, and there we are. Are you comfortable with that?
How
Now,
did you get the 1 and the 2 below the P?
what you do is you hit function and you hit that button there.
I
called the
totally
sum.
missed that.
Right? Now, P1 hat I've already got, so I'm writing it down. That's 18% from April. P2 hat was 22%. And they told us that the p-value is this number. Now, the p-hat is the probability that you got the results that you got, right? It's one of these 5 guys, and I'm just going to be lazy because it takes me too long to read these things. Now I probably end up reading the wrong one, knowing me. There you go. P-value is the probability of observing a difference in the sample proportion that is at least as large as the one observed if there was no difference in the populations. Okay, that's one way of thinking of p-value. P-value is the probability that you would get the result you got by just randomness. Be another way of talking about it. P-value could also be thought of as the probability that you would get it wrong if you said that there was evidence when there wasn't really. So lots of different ways of thinking what that one is. Now, our number for p-value is 0.012. If we use this fella, the p-value is greater than 0.05. So there is, oh, there we go, is sufficient. Hey, why do you mean there is sufficient evidence? Oh, because it's smaller, of course. It's less than that number, right? We had 0.012, and that's less than this. So there is sufficient evidence. And then they go and they give you a little story. And I want to get those things away. So that's the new question 1 that we didn't have last time. We've done the one to do with returning the money. I think I skipped the ear piercing. I'm still going to skip it. We did the dating one, didn't we? Recollect that one? Oh, this is a new one. Let's do this one. Poll was taken in October of 2019 and asked the question, in general, do you feel that the laws governing the sale of firearms should be made more strict, less strict, or kept the same? Of the 847 men who responded, so I'll have population 1 as the men. N1, there's 847 of them, and 466 out of 847 said it should be stricter, and that's 55%. And then the second population is women, and they had a sample of 679 of them, and 514 out of 679, which is a lot larger, is 76%. They said it was more strict. Assuming that these respondents are random sample of all men and women, is there sufficient evidence to conclude that more women than men thought that they should be stricter? Yeah, 76 to 55 seems reasonable. And they're using, because they're really boring, they're picking 5% again as their significance level. Okay, null hypothesis. Well, that's the easy part. Percentage of men who think it should be stricter, take away percentage of women who think it should be stricter, should equal 0. Alternate hypothesis. More women than men. Now you got to be careful. John is taller than Mary. Mary is shorter than Tom, right? Is this going to be a greater than, a less than, or a not equal to? And I have just seen something that caught me out. The little darlings. Do you notice that they're doing women take away men? Even although the information was given as men then women, they decided to play with my brain and do women as 1 and men as 2. So bear that in mind. What's that going to be now? Greater than, less than, or not equal to?
Less than.
So if it's less than 0, that means the percentage of women take away men is a negative number, right? It's less than 0. Where men, let's phrase it this way. Which one was the bigger, men or women?
Women.
Right. So if women is a bigger number than men, won't the women number take away the men number be a positive number. Does that make sense?
Yes.
So that's maybe the kind of way you should ask yourself that question, because it looks like they're like throwing them in the air and jumbling them, you know, like that shell game where you're trying to keep track of who's first and who's second and where's the little shell thing gone, right? So now that you've got that set up, there are two independent samples, and they're doing the, do you know the test about the number 10 test? Remember how that works? Was there at least 10 people who said yes? Was there at least 10 people who said no? Does it pass all those? Yes, it does. We can assume that it's randomly selected, and all of these numbers are both at least 10, so we can conclude that the conditions are met, right? Can you remember what I talked about when I say the 10 test? It's just a shortcut for NP and N1 minus P have to be bigger than 10 for both samples. Right, now we're going to do p-value. So I'm going to have to hit salt. Not good, but nonetheless, I can still do it. Two sample proportion. Number of successes was 400 and, oh, it's women first. So it's 514 women out of a total of 679. And for the men, who's going to be number 2, it's 466 out of a grand total of 847. And we decided that women take away men is bigger than 0. And we generate a result. And can you see that p-value is so small, it's negligible. Right. Now, I can't go back to the original question because salt did that annoying thing of it rubs out my WebAssign and it puts salt in there. I think it's my browser that may be to blame, but I can't recreate it. But would you agree that that is enough evidence to prove that women are more in favour of stricter gun rules than men? And that would be your, you know, some kind of finishing answer along those lines. Hey, I take it back. Look, it's hiding. It's under it. Yay. Cool. I'm happy again. Oh. Interesting. America's got this thing about guns that I don't understand. This is true. Guns scare me. I do not like seeing them. I remember the first time I came to America, and I was walking around in a supermarket picking up some stuff, and there was just a cop there, a policeman, and he was just, you know, getting his lunch or whatever he was getting. And I couldn't stop staring at his gun because it was just weird. Just totally weird to my brain because I'm not used to guns. I've never actually held a gun in my life. I've never touched one. Don't like the damn thing. Scare the EBGBs out of me. Americans like guns. That's fine. I'm a great believer in people choosing what they want to do and what they don't want to do. So I kind of like it. But don't give me a gun. That wouldn't be a good idea. I would not be a good person. The safest person would be the criminal that I was trying to shoot. I'm pretty sure of that. He would be pretty safe if I had a gun. Oh, it's tragic the number of things that happen. Where's my brain going with this? Yeah. I know a lot of people think they should ban guns. I can understand it, especially when there's tragedies with lots of people getting killed. But my logic tells me that if you want to fix that problem, banning guns probably won't do it. Because if you ban guns, won't only honest, law-abiding people give back their guns? Do you think gangs will give up their guns? Murderers give up their guns?
Didn't
Crazy
work with
people.
alcohol.
Say that again, Orion?
It didn't work with alcohol.
No. So, I mean, you'll feel better. I made a law and I passed it. I don't know what the solution to that problem is, but banning things doesn't tend to work. I mean, you've banned drugs for how long? Since year zero. Have drugs gone away? So I guess banning it really doesn't do much. Interesting thought. Don't know where that came from, but never mind, it's here. Let's look at our next question then. A case control study compared short to not short English secondary school students. Oh, you mean the height of them? I was trying to get the sense of that. So they had 98 students who were a bit on the small side. 48 of them said they had been bullied. And 115 who weren't considered short, 30 of them had got bullied. So this is like a social science, a case study where they're looking at what factors cause bullying. Right. So evidently size might be one of them, right? Small people get picked on. Right, that makes sense. If you're 6'6" and got muscles, do you think somebody's going to come over and pick on you? They probably aren't going to do it as often as if you're 5'2" and you weigh 100 pounds. So I'm just being exaggerating here. So I can understand, not bullying is just totally wrong, but I can understand where this data's coming from. Okay, so what we have is pretty much all the information given to us. Short people, 48 out of 98 get bullied. That's your P hat there. 30 out of 115, that's your P2 hat. The difference, which is what that is. Have you noticed that they call it P1 bracket, take away P2 bracket, but you can't use that in WebAssign? That is not, that's just not right, is it? I mean, it's okay for them to do a bracket, but you can't. It doesn't seem fair. Anyway, there's a thing called the lower bound, which we haven't talked about yet. But basically, it's like a 95% confidence interval, but it's only got one side that is actually variable. And so when they talk about a lower bound to 95, this is the small number, comma, the big number's 100%. So it's a very special kind of confidence interval. It's a 95% lower bound confidence interval. Pretty rare, but this textbook likes it. There's your Z and there's your p-value, right? So pretty much everything you could want and probably some stuff you don't want. So we're going to assume this time, good, short, not short. So yay! I remembered that from last time, so it was still there. Hey, right? One takeaway, two. Now, in this case, are you agreeing that short people get bullied more than tall people? So we're looking for evidence that it's greater than 0. Right? Little people more bullied than big people. Now, use the computer output. Oh God, I hate it when it says use computer output. So I'm going to use SALT. Okay, so I got all the numbers. Yeah. So I'll just steal this fella. Bring over here. 2 sample proportion. And for the short people, write that down. 40, 80, 98, and for the taller people, 30 out of 115. And we'll hope that this hasn't got anything to do with binomial. 48 out of 98. And for the taller people, it was 30 out of 115. And we want to prove that it was small people get bullied more than big. There's our guy. That is a tiny p-value, would you agree? And so that is definitely going to be statistically significant. Let me find where my question is now. Is it here? Oh, I've lost my question. Yeah, here it is. And the test statistic, I've forgotten what it was. It's that guy. It's that guy. The p-value was 0 point, lots of zeros and a 1. And then can't we just oops, finish this one? Since the p-value is less than the significance level, we would reject H naught. This means that there is sufficient evidence to conclude that short students are bullied more often. Great. Tiny p-value, we are good. Now, remember that funny thing up here, the 95% lower bound guy? This is new. So this is the small side. Right, wouldn't a normal 95% confidence interval be this number and maybe the other number is 0.246? You know, so it would be a start number and a finish. That's your typical 95% confidence interval. But in these ones, a one-sided, you've got the number that would vary, but the other side's just 1. What that is telling us is that the p-value, or in this case, the difference between the proportions, is somewhere between that or bigger. Right, we're 95% sure it's that number or something even bigger than that number. So that's what the 1 is about, right? I mean, the difference could be total, you know, everything. Now, since the confidence interval falls entirely above 0, the null hypothesis should be rejected. Remember, we did confidence intervals, and if everybody was positive, that meant one thing, and if everybody in the interval was negative, that would mean another thing. But if it contained 0, that was no evidence. That's essentially what is happening here. Would you agree that all these guys are positive, right? They all are above 0, and that's equivalent to saying we should reject it, right? We go with that. If the interval contained negatives, we would go somewhere else. Here is basically a different kind of confidence, a different type of hypothesis test. And it's looking, it's just put the data in the form of a table, essentially. So read over the intro, and then we're going straight into solve. Studies have suggested that alcohol abuse and disorders are found to be more prevalent during early adult than any other age group. That's a bit scary, but 9% of young adults, that's 18 to 29-year-olds, could be labeled as alcoholic. So they must have some rule about how many times you get drunk a week. And if it's this number or a month, whatever it should be, that would constitute an alcoholic in their terms. In addition, surveys have shown that college students tend to drink more than their peers. So if you lot go to university, Olivia, you keep away from the whiskey, right? James, I do not want to hear stories. What is it? Pullman has got a reputation for partying too much. Which one is it? Olivia, you're nodding. Is it Pullman?
It is
Right.
Pullman.
Right. None of you go to that one then, right? What does Evergreen have a reputation for doing? Smoking marijuana, I've been told. There's a lot of tree huggers there, I've been told as well. I don't know if there's any connection between those two things. So don't go there, would be my advice. Okay, now being silly. Right, here is all the data that we need to do. Let's look at the superficial data. They looked at 250 adults attending college, and they looked at 160 who weren't at college. And they asked them a question about being drunk, essentially. And so if that number is big compared to this, then that's the percentage of them that drink too much, right? What they're considering to be drinking too much. And this one. If you did this one with Scotland, I think the numbers would be much bigger. So I put that in there. So I'm going to have to take note of all these numbers. Essentially, the numbers I need are 92 out of 250 for the first group. That's the college students. And then the second group is 48 out of 160 drink too much. And that is the second group. And then I'll do the test statistic, which is the Z-score. So use Salt. Bring this guy here, click on it. To proportion. The number of successes, I wouldn't call it success, but 92 out of 250. That's how many college students got drunk. And 48 out of 160. Are we comfortable about those numbers and where they're going? College and then non-college. And we're being asked here to test to see if there's a difference. So we're not being asked to test, is it bigger or is it less, but just that they're different. And because of that, won't we use a not equal to? Even although the data probably strongly suggests that the college students drink too much, we're not being asked to prove that. We're only being asked to prove that they're different. So I'm going to generate results. And that is interesting. Isn't that p-value of 0.15 pretty big in the big scheme of things? Would that be not enough evidence to reject the null hypothesis then? So at least according to this survey, it may be thought that college students drink more than people who don't go to college, but there isn't really any evidence right now, at least, to prove that. So I'd go back into this question. The test statistic that they're talking about is the Z-score. I know you can't see it, but I'm just going to copy and paste it. It was that number, and to 2 decimal places, it's that number. And we would fail to reject the null hypothesis. Isn't that the choice based on the p-value that we've seen? Remember the 0.15, just too big. In fact, wouldn't it fail no matter what we did? Because there are only 3 that you should use, isn't there? A 10%, a 5%, and a 1%. And it's bigger than all of those, so you would fail to reject. Question 8 is basically the same kind of story, right? Table of values, plug it in a similar way, same kind of questions. You feel comfortable that you've seen 7, you should be able to do 8. Right, that's kind of the end of the difference between 2 proportions and hypothesis tests on them. Any questions before we move on? Do you feel comfortable now about the process? How to take a written story and for the most part use salt. Occasionally you do some calculations by hand, but mostly using salt. Feel good? Now, that process that we've used is not a dumbed down version of what the real people do. That's what real scientists do, and real social scientists and political science people and medical clinical trial people. That's essentially the process, right? You're not allowed to create your own process. You know, this is how I'm going to test my data and this is how I'm going to come to my conclusion, because it'll never get published. It just won't be accepted in the scientific world. So we're kind of forced to use this hypothesis test. But at least that means Olivia and James and me and Nathan and anybody else, if you are in the medical field and you see, you read an article, they will give you this kind of data and they'll probably put down the p-value as 0.07 and you'll say, okay, that would work on a 10%, but you know, that's a 7% chance that what I'm reading here isn't really true, right? Remember, your p-value has different meaning, can be thought of in different ways, right? I like to think of it in that way. It tells you, when you see, yeah, there's evidence, it tells you the percentage of the time you're going to get it wrong. And if you're interested in the theory, it's called a type 1 error. So if you want to know what it's called, that's what it's called. I got a chat here, so that may be a question. I don't know, Sydney. Did I answer your question, Sydney? You were asking about the null hypothesis. Are you okay with that now?
Yeah.
Okay. So let's move on then, guys. I'm closing a whole load of windows here. Hopefully I don't close too many. That's p-value. I don't want that, go away. Okay, we are now moving on to our second last section. We're almost done. It's kind of cool, right? If you give me a few moments, I'll be writing it down. So we're going to be looking at chapter 13A, and it's hypothesis testing. About a single mean. Okay. Not sure. Go in here. Advanced. Yeah. That's the guy we're going to be looking at. At least I'll do the intro today. I'm not sure how far we'll get. The next couple of days, things are going to be pretty hectic for me. I have various doctor appointments and dental appointments, and they poke me and suck my blood and all sorts of things. It's just not right. Okay, so we are going to be doing, the reason I was going to say that is that they're not going to be any officer today. I'll be going to get my teeth filled. Yeah, I think I'm getting a filling, or I'm getting a crown, or I'm getting both. I'm getting something, can't remember what. So I have to leave for that. I'm not sure if I'll do a 5 o'clock one like I did yesterday for an officer. It depends on how much drugs they give me and how much damage they do. I might not feel like drilling while I'm like teaching. So I'm probably not going to do it. And tomorrow, we won't be doing a 10 o'clock one because that's 10:30 is when I'm off to do a different thing. So I'll be moving this one up to probably the 12 o'clock time slot. So if you want to see the kind of continuing story, you'll have to drop in then. So let's get a start on this. We're going to have population again. and we're going to be looking at a parameter. A parameter, remember, is a number that you get from the entire population. And the parameter we're going to be looking at is called the Greek letter mu. That's how you pronounce it. What does the Greek letter mu represent for a population? What is it? If I said the population mu equals 20, what am I telling you about the population?
It's me.
It's its mean, right? Which kind of is obvious when you look there, right? Now, we would like to do a hypothesis test looking at, has the mean changed? Right. So can you imagine that it used to be that the average IQ, right, the mean IQ of Scottish people was 101, right? Say that as granted. But we now believe that it's changed. And we think it's got less. So although all that drinking that they've been doing over the last couple of decades has dumbed down the Scottish population, and we think it is less. So how do we prove it? Well, don't we find a sample? And when you do a sample and you get a number from it, that number is called a statistic. And for every parameter in a population, isn't there an equivalent statistic from the sample that is measuring the same kind of thing? So what do we call the sample version of this guy?
Sample proportion.
Oh, are we talking proportions anymore?
Oh.
So what do we call it then?
Sample mean.
Correct. So how do we test? Has it changed? Well, we go and get a sample and we find its mean. And then we try and see whether there's any statistical difference between them, right? So we're going to have a null hypothesis and we're going to have an alternate. And the null hypothesis is that the mean IQ is still 101. And the alternate in my story is that it has now gone down. Do you see that when you do a single mean story, you have got what it used to be and then what we believe the change is? Would you be surprised to find out that there are 3 hypothesis versions? This one is called left-tailed. In a different story, oh, in fact, let's do different numbers to emphasize that. Totally different story. In this one, wouldn't you be looking for evidence that the mean has increased? It's got bigger than it used to be. What name do we give to this one? If this is called left-tailed, what do we call this fella?
Right-tailed.
Can you remember from yesterday, somebody went and said it in a very, to me, it seemed a very clear way. How you tell? How you know to call it a left or a right? What was the short way that they remembered? Can you?
Which way the greater sign is pointing?
Yeah, pointing to the left, pointing to the right. Does that help? Here's another way. Less than is left. L, left than, less, right? That's another way of doing it. And the third possibility, pick a different number again. Is that you're looking for evidence that it's different, that it's changed. But they don't mention which way, just that it's not the same as it used to be. And that's called two-tailed. Isn't there a remarkable similarity about what we've done here and what you did in single proportions? I mean, it's very, very similar. Only here you don't deal with decimals. Here, don't you deal with real numbers, typically bigger than 1, right? 42 and 17.9 and 83 and 102 and whatever, right? Whereas when you did proportions, wasn't it? P equals 0.2 and P is bigger than 0.2, right? It was always a proportion, which means it was a 0 to 1 number. For a single proportion, a positive 0 to 1 number. For a single mean, it's a positive number typically. And here are our 3 guys. So, continuing with my story then about IQs and Scots people, let's suppose that we found a random sample of 200 Scottish people and that their IQ was 99, right? Their average IQ was 99. Now, superficially, would you agree that that is evidence that it has reduced, right? It's not 101, it's definitely less than 101. But we've hopefully got to the point where we know that that might just be randomness that you get whenever you pick 200 people. Couldn't I do another sample of 200 and the average is 102, right? Things vary. And so we need to calculate, mostly by using salt, how unlikely that is. So let me put a significance level of 0.10. So that's a 10% significance level. I'm going to do a number of calculations by hand that you typically would do in salt, but at least I want to show you what it would look like, you know, by hand, just so you get a feel for what the software's doing, or at least as much as I can. Now, you also are going to be told the standard deviation of the sample. And let's say the standard deviation is 12. So you found 200 Scotsmen, the mean is 99, and the standard deviation is 12. And we are interested in this hypothesis test. It used to be 101. Is there evidence to show that it's gone down? So we need to collect some numbers in order to get a Z-score or a T-score. It would be a T-score in this case, for a normal sample, right? So there is a guy that you have met before called the standard error of the sample mean. You remember that guy? So here's the biggie. How good is your memory? What is the formula for the standard error?
Is it the standard deviation over the square root of the sample population?
It is. Does that ring bells? It's not different formula. Aren't we using the same formula, but in different ways? Right? We're using it for different reasons. Weren't we using that to get confidence intervals last time? We're not doing confidence intervals, aren't we? We're using a new thing, right? Hypothesis testing, but we're still finding the same kind of things. Now, on my calculator then, we have 12 divided by the square root of 200. And the answer I get in this case is 0.849. That's the 3 decimal places. Now, I'm going to be doing this question in salt. So I'm going to cover myself right now. Can you imagine that when I do this in salt, aren't we going to have some rounding off differences? Because salts, I don't want to have to write things to like 12 decimal places. I just don't want to do that, right? I'm being lazy. But if I did do it to 12 decimal places, whatever number that's there, wouldn't I get exactly the same answer as salt, right? So don't be put off by it's a little bit out. So far, so good. Now, the guy that we're going to get is our T guy, right? He's what we are calling the test statistic. In proportions, wasn't the test statistic called a Z-score? But when you do means, right? Population means, sample means. When you do means, your test statistic is almost always going to be a T-score, right? So that might be, it's a label, I guess, but it is important. Now, it's got a formula. And here it is. Well, I know X bar, it's 99. Not quite sure who he is yet. And the standard error is this guy. Mu naught. In population proportion ones, wasn't there a guy called P naught that we kind of touched on once, maybe twice? What number is mu naught? He's actually in this piece of paper here. What number is mu naught?
101.
Right. Are you happy about that? That's just how the formula, because won't this change every story? You know, the next story that's 82, and then a totally different story, it's 41. So what they're doing is they're basically calling that guy, you know, right? They're giving him a name. I'm not going to do the mistake this time, but remember of order of operations, 99 take away 101 divided by 0.849. And the answer we get here is negative 2.36, roughly. T-scores are very, very like Z-scores. The only major difference between the two is that T-scores tend to have a bit more variation in them. In other words, they tend to be bigger positive numbers and bigger negative numbers when the samples are quite small. Once the samples get really big, the T-score and the Z-score, if you calculated a Z-score instead of a T-score, they pretty much merge together, right? So T-score is what you do because the data isn't necessarily perfectly normal in shape. So because of that, you add a little wiggle room by making it a little bit bigger. Now, at this point here, the next thing we would have to calculate is a p-value. But once you get to that stage, it's really impractical to do it by hand. So we are going to now do salt, and we're going to get the p-value. And I now have to go hunting, hopefully. Okay, I'll put that guy there. 13A, gonna view it. Okay, I think I'm ready. Okay, I'm just using this to get salt up. Here's salt. And now we have some new decisions to make. This is a hypothesis test, isn't this? All of them are hypothesis tests. So this is not the right tab. Where should I be right now?
inferential.
Right. Now, do you see this guy is called one sample t? That's actually what we want. Single means are one sample t's. Aren't single proportions one sample proportions? Aren't two sample proportions, right? Single means are one sample t. When we do the last section, we'll be doing the difference between two means. It'll be called two sample t. So one sample t. The mean in this case was 99. The sample was 12, and the sample size was 200. The hypothetical mean is just their way of saying what it used to be. And aren't we trying to prove that it has decreased? Are you comfortable with one sample t, the sample mean, the sample standard deviation, the sample size? Basically, h naught equals 101, but we want h naught, we want to prove that it's got less, right? So when I do generate results, can you see our nice h naught, h1, ha? There is that t statistic. I had negative 2.36. I am kind of pleased with myself. This time, it's good enough, right? It worked. If it had been 2.347, wouldn't we be okay with that, right? We know that it was just rounding off that caused it. It wasn't we did anything. Now, would you look at that p-value? That is a pretty interesting p-value. 0.00, oh dear, 9697, right? I'm now going to go back to our written story and let's finish it off. We want to do this guy. I think I should round this guy off. Now, I was going to round this guy off to 3 decimal places. And if I do that, something rather weird happens. Are you happy about to 3 decimal places, 009697 rounds up to 0.010? Are you comfortable with that? It's a little bit weird looking, but that's rounding off. Now you might say, why do I even bother with the 0? Well, normally if you round off to 3 decimal places, you should show that by having 3 digits. That's all, right? Okay, now it's time to do our test. Is our p-value less than our significance level? Is our 0.010 less than 0.10? Yes or no? You're nodding, Olivia. Are you nodding for yes?
Yes.
Okay then, so I agree with you. Won't the conclusion then be that, I'm doing a very abbreviated version because I'm running short of room, is that we can reject H naught? Doesn't that mean that Scotsman's IQs have actually fallen over the last 20 years, if that was true data? If you put a population, a single proportion population hypothesis test, and you compared it to this one, wouldn't there be more things in common than dissimilar? Would you agree that the process has very much got the same pieces to it? You're just going to have to do this instead of decimal, and won't these be numbers rather than decimals? Won't you have a different calculation for the standard error? But most of that is done, including the t-score, isn't that done inside SALT, so you don't even notice that? But just to show you that's what's happening inside SALT, so it's not total magic. What you're finding in the p-value, if you're interested in, is that the p-value is the probability that you get a t-score less than or equal to negative 2.36. So we're basically finding out how unlikely is it to get that t-score? And the answer is, it would probably happen about 1% of the time by sheer randomness. And since that is so small, that really means that we've got evidence to prove that the IQ's gone down. Now, if that number here had been 0.14, right, 14%, wouldn't we fail to reject the null hypothesis? And we'd say, it might look to you like Scott's IQ has gone down, but there's no statistical evidence that that's true. The number you got was very likely just the usual randomness that you always get. It's pretty powerful, isn't it, that you can take a limited amount of information, but to come up with such useful conclusions. And you could send it to anybody and they would agree with you, right? Provided you know the rules. So for what's left of today, because as I said, I've got other business, I'm going to give you a kind of preamble to this. What am I talking about is, when can you use this method? And when you shouldn't use it. When you did proportions, were the rules something like it had to be a random sample, right? And didn't we have the 10 rule, right? NP had to be bigger than 10, N1 minus P. In other words, the yeses should be at least 10 people said yes to the question and at least 10 people said no, right? And that was pretty much it. It wasn't that big a hurdle to go over, right? Those kinds of questions tend to be quite common, but we have slightly different requirements when you're doing means. First one is it should be a random sample, not a surprise there. And while I'm at it, I'm going to put in, we're assuming that it's unbiased, right? You didn't just go to Scotland and find the dumbest looking ones and test their IQs, right? It was, it was all sorts of good mixture. That's pretty standard. You wouldn't expect that. There is a requirement for sample size. This one is not as good. I like the 10 rule. Can't everybody say NP is bigger than 10 or equal to 10, N1 minus P bigger than equal to 10? It's a calculation. Nobody can argue about it. Everybody's kind of, got together on this one and said 10 it is. Sample size, not so good. Round about 30 or more. You really shouldn't be doing hypothesis testing with 10 people. Can you imagine that's probably far too small to be really comfortable about any conclusions? Yet some people do it, unfortunately. So as a very, very rough rule of guide. Now, if you have 29 people, yeah, you could probably do it, right? You should feel uncomfortable, but not that uncomfortable that you're not even going to try, right? Third one is totally different that you wouldn't do. The population that you are looking at, that you're going to do this hypothesis test, should be approximately bell-shaped, right? Normal in shape. And approximately is a nice vague word. It would be really nice if that was the population. That would be perfect to do these things on. That's good. It is allowed to be a little bit out. This is such a useful process that we don't want to be too strict and never use it, because would you agree that in the perfect world, nothing's perfect? Nothing's perfectly normal. Real data is never perfectly normal. So you got to allow a little wiggle room, right? So you can be a little bit skewed to the left, you can be a little bit skewed to the right, as long as it's not extreme. That's okay. I'm trying to over-exaggerate it. Can you see that that is a really skewed to the right? Not okay. If you try to do this hypothesis test, you would get numbers and you would get p-values and you would get whatever you got and you would have conclusions. The conclusions are untrustworthy, and they're untrustworthy because it's broken the rule that it should be approximately normal. Can you see that there is a lot of gray area between the okays and the not okays? Because what Olivia might think is, yeah, it's skewed to the right or the left, but it's only a little, and I want to be able to do this because if I can't do this, then I'm stuck, right? I can't prove anything. So there is a kind of motivation, I want to do it. James, because he had or was going to have lawyers in the family, would say, I'm a stickler. The minute it goes by there, I ain't allowing it, right? Which means that when they do statistical analysis and hypothesis testing, it's fraught with danger. I have looked at data and I've superficially saw what it looked like, and I'm shaking my head and I'm thinking, why on earth did they even try and do hypothesis testing this? This data has definitely got problems. And if the data's got problems, won't the conclusion have problems? I mean, that kind of common sense. There are other no-nos. Would you think that is okay? Agreed. Bimodal data, right? Two hills is really bad. Don't do it, right? Danger, Will Robinson, just don't do it. Of course, there are gray areas because the world is not perfect. Theoretically, isn't there two bumps in that? That one would be okay. Can you see the gray area between definitely not and yeah, there's a little bit of a bump, but it ain't that bad a bump that I can't live with it, right? Now, these are things that they don't go into in the homework, but I think these are important to know that if you ever go into a field where there's experiments happening and they're collecting data and they're trying to prove something, right, doing a hypothesis test, that you have that skeptical viewpoint of, before I even look at what you did, can I see what your data looked like? Can I at least see that? And what you can typically do is that if you look at the sample, it won't be a perfect match to what the population looks like, but won't it be a reflection of what the population looks like? So if my sample has two distinct bumps to it, right, if I had a big enough sample to see that, would you agree if you built a little histogram of it and it had that shape, wouldn't you be kind of worried about it? Right. And the last one is Bill Gates. Actually, outliers. Can you imagine that you had your sample? There's Bill Gates, just on his lonesome. What does a Bill Gates outlier do to the mean? Doesn't it make it huge, much bigger than it should be? And if you make the mean much bigger than it should be, can you see that the way we calculated this, isn't that going to disrupt the whole calculation? And at this point, we get into a different problem. Scientists recognize that outliers are bad news. Some outliers just happened because you were measuring and the machine wasn't calibrated right, and it chucks out this number that's 100 times bigger than everybody else. And you kind of say, yeah, we should have checked that machine before we did it. It's just an anomaly. It's not really true. And what they do is they kill it. And they use the other 200 numbers. Now, that is a valid thing to do if the outlier is considered not representative of the population. But can you imagine an unscrupulous person who kicks out data because it doesn't fit what they want to be true? Can't you then throw things out as outliers when really they're not outliers? Aren't they just lots of guys belonging to this tail? You're not allowed to go here and say, outlier, 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 outlier. Now I have a nice distribution and I'll do it with that. So if you are being honest, sometimes you cannot do the test. Right? You shouldn't do a hypothesis test. It might mean that you have to start from scratch. Right? Just do it again. It might mean that maybe this isn't the way to analyze this result. And there are lots of other ways in statistics to analyze results that fall into the not okay category, right? You can do it in other ways, right? Much more complicated, but that doesn't mean that it's not possible. And that's going to be me for today. Are we good? Did we learn